In this recording, we're going to build on what we learned in the first part of this video about e as we learn about its inverse, the natural logarithm. And so as I had said before, a way that I have come across that I find is very intuitive is to think of, all right, this is a growth function, right? It has a base of e, which is about 2.72, right? So this is growth. That's what e to the x tells us. How much growth we have after time x. Natural log flips it around. It says, okay, if you want to know the time it took to get x amount, that's we use the natural log. All right? So e to the x tells us growth. Could be a decay, right, if x is negative, or the exponent is negative. Natural log tells us amount of time to get to that growth. All right, so check this out. We got something like this. It says, all right, well, you can do this without a calculator. Find natural log of e, and you might look at that and say, I can't even begin to figure that out without a calculator. Well, let's do it this way. We set up here, natural log of x is really log base e of x, because every log has a base. So if I rate log base e of e, well, there's a 1 here, right? Put it out here. This is saying, what exponent do you raise e to get e to the 1? Of course, that would just be a 1, right? And this one, natural log, is the same as log base e of 1. So this is saying, okay, what exponent do I raise e to get a 1? And there's one exponent that you raise anything to get a 1. Of course, that's 0. All right, see if you can figure out parts C and D. Play the recording when you're ready. Okay, so this one says natural log of e to the 5th. So what's the exponent I raise e to get e to the 5th? It's kind of like saying, when's the 6 o'clock news on, right? It's kind of a rhetorical question. So that would be a 5. And then finally, this one's a little bit tricky because we have to represent square root of e as a fractional exponent. So if you remember, square root of e is the same as e to the 1/2 power. There's a 1 here and there's an implied 2 out here, so power over root. So if I do natural log is log base e of e to the 1/2 power, hopefully that helps. So e raised to the 1/2 gives me e to the 1/2, so 1/2. In other words, the e and the natural log are inverses, so they undo each other, right? They undo each other, so I just simply get the exponent. And this is a great example in part C. It's probably the most clear one. Okay? We're going to skip exercise 4 for now with our log properties and get right into this cooling problem. Very interesting question. Okay? So read through the problem and play the recording when you're ready. Okay, so hopefully you took time to read it. If not, please do so now. Looks very complicated and intimidating, right? But here's what we've got going on. We have a time, which is represented by m, measured in minutes, and the big T tells us the temperature in degrees of our particular hot liquid. Okay? So maybe as we explore this a little bit, we'll get a little more familiarity. Let's start out with question A, where it says, what's the initial temperature of the water at m equals 0? So no calculator here. Just substitute in, work out. Play the recording when you're ready. Okay, so you should have T of 0. Just make your substitution. Okay, so e to the 0 we know is a 1, right? So that's just a 101 plus a 67, because e to the 0 is a 1, so it's just 101 times 1, right? Add those numbers up, and we've got 168, well, watts. What is this measuring? Minutes? Hours? What? I have to go back to the definition of T. T is measured in degrees Fahrenheit. Okay, so we were trying to solve for the initial temperature of the liquid, or it says the water here, right? All right, so it starts at 168 degrees, and because it's e to a negative exponent, it's actually not growth, it's going to be decay. And that makes sense. The hot liquid is in a room that is not hotter than it, so it starts cooling to match the temperature of the room. All right, what are you going to do with this statement? Take a moment to read part B and then play the recording when you're ready. Okay, so for right here we've got T of 60 equals 83.7. So 60 is M. M is the number of minutes. T is telling us a temperature at that amount of time. Okay, so we'd simply say something like this. Okay, so at that time, after 60 minutes, the temperature of the liquid is now 83.7 degrees. That's how we interpret this. So there's a couple things we can do with this. We can use this function to evaluate, like we said, evaluate growth, or in this case decay. At any amount of time, we can sub in and find out the temperature of the liquid. More interesting question is, all right, I want to know what amount of time it's going to take to get to a particular temperature. Okay, so we're going to use the natural log in here, right? Because natural log finds us time to get to a particular amount. All right? So, reading through this problem, it says determine algebraically when, so that's a good clue, we're going to solve for amount of time, the temperature is going to be 100 degrees. So, okay, so the 100 degrees is my temperature here. All right, and the time is unknown. This is a pretty tough one, guys, but we can figure it out together. I see three different, maybe four different operations that are affecting the T. You've got a plus 67, you've got 101, you've got an E, that is its base, and then you've got this negative 0.03 times T. So you can kind of think of that all together in parentheses. And this is a way to think about it. So you're just thinking about your order of operations, your PEMDAS. And we're going to undo them as we solve, working our way from bottom up. Alright, so we're going to undo the addition, we're going to undo the multiplication, we're going to undo the exponent, and then finally we're going to undo what's in parentheses there, that final operation. Alright, so let's work this out step by step. So the first thing is let's subtract the 67, get that over to the other side. I'm not going to show that step, but I'm just telling you. Okay, so we subtract the 67, we got 33. Okay. And now I have to undo the multiplication, so I'm going to divide. Those divide to 1. At this point, I'm going to leave that because it's not going to be a rational number. I'm going to leave that in fraction form. And I'm right here. 33 over 101 equals e to that exponent. Now I'm kind of stumped here, but if you recall, when we're stuck with logs, guys, we go to, when you're stuck with exponential form, we go to log form. Alright, so let's go to log form here. We know the base, we know the exponent. So, cruise over here. So we're going to go log with a base. The base is e. Set that equal to our exponent. The exponent is, so log base exponent. And then the 33 101 goes right into place here. This is all just numbers on the left-hand side. I could put it in the calculator right now if I wanted to. And then obviously, the left side is pretty simple, right? I'm mixed up. On the right side is pretty simple. We're just going to divide by the negative 0.03 to get t by itself. So I showed a fancy way to write natural log of e. Now I'm just going to divide by and I'll have t. So at this point, we're going to go to the calculator. Alright. Now I think it's going to be a little more than a minute, right? An hour, right? Because it took an hour, excuse me, after an hour it had cooled from 168 to 83. So somewhere in between there, it got to 100. So that's using a little intuition. I think it's like less than an hour. Between 0 and 60, probably closer to 60, wouldn't you say? It's 100's a little closer to 83, so I'm guessing somewhere close to 60, but less than 60, maybe 40 or 50 minutes. So let's check that out. We're going to go to our calculator. We're going to do natural log. Actually, let's create a little fraction. So just double check that everything is entered correctly. I hit enter. And our prediction wasn't too bad, wasn't perfect, but 37.3 minutes. Pop over here, make sure we're rounding it right. It says round to the nearest tenth. So 37.3 minutes. And again, I can check this if I wish. I can substitute this number, 37.3, back in here for m, and it's going to come out really, really close to 100 degrees. Thanks for watching.